So to put the last movie in context, scientists had observed spectra from hydrogen and had explained the spectra, the idea that only certain energies of light were absorbed or emitted, depending on which type of spectrum it was, by saying that the electron can only have certain energy levels, and then explaining those certain energy levels with a nice solar system model in which the nucleus of the atom is the equivalent of the sun, and the electrons can only go around in specific orbits. And that was wonderful, and people celebrated, and Niels Bohr won a Nobel Prize for it, and all kinds of stuff. But of course, hydrogen is boring, it just has one electron. What about higher atoms, atoms with more than one electron? Well, the first thing to try to do was, of course, to try to explain it in terms of that same orbit model. So let's think about that. There's our nice little orbit model, okay, nucleus in the middle, first orbit, second orbit, third orbit, and so on. And we say that the hydrogen atom, when it's in the ground state, the electron is in that first orbit there, okay? And let's put a little description on that. Instead of saying that that one electron is in the first orbit, let's put n equals 1, so that's the first orbit, 1 electron in there. So it looks like n equals 1 to the power of 1. It's not. It's actually saying 1 electron in that first energy level. Well, now let's think about helium. Helium has got 2 electrons right there. Okay, this nice periodic table from the RSC again. I absolutely love this periodic table. It's awesome. So 2 electrons in a helium atom. Well, the first electron is presumably going to want to get as close to the nucleus as possible, so we'll go in the first orbit. How about the second electron? Where would that second electron like to go? And the answer is, of course, it would like to go in that first orbit. It wants to get as close as possible to the nucleus. So let's put it there, right there. Okay, can it go in there? Yes, it can. There's enough room in this little orbit for 2 electrons. Of course, the planetary model falls apart there because you don't have more than one planet in the same orbit, at least not in this solar system. But there's no reason why you can't have 2 electrons in the same orbit. So we'll say, right, helium, 2 electrons, both of those in that first orbit, both of those in the n equals 1 orbit. Or now that we're sort of moving on a bit, let's start replacing the word orbit by shell. So anyway, how about the next atom, lithium? Lithium has got 3 electrons, okay? Now, that third electron would love to go into this first orbit, but the trouble is that first orbit's a rather small little orbit. That first shell is a rather small shell. 2 electrons, no problem, but trying to stick a third electron in there, it might get a little bit cramped. And so that third electron will go into the next orbit up, or the next shell up, the second one. Okay, so lithium, we would describe it as being n equals 1, 2 electrons in there, and then 1 electron in the second shell, n equals 2. And what we're just doing there is we're applying the so-called Aufbau principle, which is the German word for building up. We're building up from the bottom up. We put electrons into the lowest energy available shell, or the lowest energy available orbit. So lithium, 3 electrons, 2 in the first orbit, 1 in the second orbit. Next one is beryllium, 4 down, only 118, 114 to go. Super stuff. 4 electrons, maybe that 4th electron can also go in the second orbit. So 2 electrons in the first orbit or first shell, 2 electrons in the second shell. Now let's go to boron, number 5 there, 5 electrons. So the first 2 electrons will of course go in the first shell. The second 2 electrons, no problem, going into the second shell. What about that next electron, that 5th electron? Well, of course, after we'd put 2 electrons into the first shell, we were finished. That shell was full because it's so small. But the second shell's bigger. Absolutely no reason why it can't handle at least 3 electrons. And so the 5th electron there pops in to the second shell, electron configuration of boron, and that's this fancy word we're doing. It's the shell electron configuration. 2 electrons in the first shell, 3 electrons in the second shell. Neon, which of course is all the way along here, we can actually put quite a few, up to 8 electrons in the second shell. And so let's put those electrons in there. So 2 electrons in the first shell, second shell bigger, it can accommodate 8 electrons. So neon has 2 electrons in that first shell, 8 electrons in the second shell, and at that point that second shell is full. And you can actually start to get a little clue here, and this is a spoiler, right? Neon there, right at the end there, the second shell is filled when we get to neon. Now, overall, it was calculated that the maximum number of electrons, of course, increases as the shell gets bigger, but it's not just a random increase, it has a nice little pattern. You can put 2 electrons into the first shell maximum. You can put 8 electrons into the second shell maximum. You can put 18 electrons into the third shell. You can put 32 electrons in the fourth shell. You can put 50 electrons into the fifth shell. Now pause and see if you can figure out what the pattern is. I don't have to pause because I can just keep talking because you can pause the video. So if we talk about the nth shell, well then you can have 2n squared electrons in that nth shell. So let's just exemplify. First shell, n squared is 1, 2 times 1 is 2. Third shell, n is 3. 3 squared is 9, times 2 is 18, and so on, and so on, and so on. So we have a nice little way in which we can predict how many electrons you can get into each shell, and using that prediction, that pattern, we can figure out the shell electron configuration of any atom that we wanted to. So let's go back to our periodic table and let's look, for example, for starters at chlorine. Find chlorine on the periodic table. I do want you to start becoming familiar with the periodic table. There it is right there. Okay, chlorine has 17 electrons because there's chlorine, atomic number is 17. So now let's do that shell electron configuration. We have to talk about 17 electrons. Where will they go? Well, the first 2 will go into the first shell. The next 8 will go into the second shell. 2 plus 8 is 10. How many do we have left? 7. Can we stick 7 in the third shell? Yep, we could have up to 18 in the third shell. So therefore, it's electron configuration. It's shell electron configuration. 2 in the first shell, 8 in the second shell, 7 in the third shell. Let's get a bit fancier with a germanium. There's germanium on the table, right there. 32 electrons in this one. So let's go ahead and fill that out, shall we? 2 in the first shell, 8 in the second shell, so that's 10, so we got 22 left. So how in the third shell? Well, we can add 18 into the third shell. 18 is not 22, so we'll put all 18 in that third shell, and the third shell is going to be full. And now we're left with 10 plus 18, 28. We're going to be left with 4 electrons out of the 32, and so 4 in the fourth shell. Practice that a little bit. We're not going to focus very much on it because the model actually, as we'll talk about in the next couple of slides, doesn't work very well, but it is a good way to get a rough feel for things, and certainly that's your GCSE build up of what an atom looks like. As I said, with a little bit of a spoiler, the nice simple shell model doesn't work for higher level atoms. Now there's 2 things for which it doesn't work, one of which we're going to discuss in this class, and the other one of which, the much more complicated one, we're going to wait to discuss when we get into the first and the second years of the fundamental degree program. But anyway, the first thing is that when you look at other atoms, their spectra are much more complicated. There's many more lines in it, right? Hydrogen, if we look at this particular range of the electromagnetic spectrum, there's 1, 2, 3, 4 lines in it. Sodium has got 1, 2, and then this is actually 2 overlapping lines, so that's 4, 5, 6, 7, 8. Go to calcium, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, because that's an overlapping 13, 14, 15, 16, 17 lines, and so on. Okay, so atoms that have more than 1 electron have way more lines in their spectra. And so what that means is that there's more transitions. You can't just explain it as the nice first shell, second shell, third shell, fourth shell. So the model that is adopted, and as you'll see in a little while, it matches up quite nicely with the periodic table. The model that is adopted is one in which instead of just talking about shells, we split those shells into subshells. So for example, the third shell has 3 subshells. So now instead of having one transition from the first shell to the third shell, you can have 3 transitions: first shell to one of the subshells, first shell to a second of the subshell, first shell to the third possible subshell of the third shell. The other thing is that, and I'll mention it here, but then I want you to put it out of your mind until we get into the second semester of your next year's worth of study, and that is that, remember, with the hydrogen atom, not only was there this nice little orbit model that we could use, but we could explain the energies in the spectra with that nice little equation. Okay, the energy equals 2.18 times 10 to the minus 18 into 1 over m1 squared minus 1 over n2 squared. I know it was a disgusting looking equation, but it's a beautiful, gorgeous equation, because it enabled us to very simply explain all those energies observed by the hydrogen spectrum. Well, as soon as you get past 1 electron, you cannot come up with such a simple explanation. There is not a nice cute formula with the 1 over m1 squared minus 1 over n2 squared. There's no nice constant that explains the energies that are seen in, for example, the sodium spectrum. Okay, so 2 issues. The first is lots more lines, which we can accommodate in our model by splitting shells into subshells, and then no easy way to rationalize the energies. That has to wait until we get into next year's worth of study. So because we're looking at the distinctly simplified way of doing things, there's no good rational way to talk about shells and subshells other than to do it in terms of the periodic table. Okay, here's the periodic table. Beautiful, wonderful, best way to present it, the most fundamental central concept in all of science. I mean, it's absolutely wonderful, isn't it? Well, now if we look at the periodic table and we start breaking it down a little bit, first of all, let's look at the rows. We have the first row has got 2 atoms wide. Okay, the next row 8 wide, the next row down still 8, but then we get on to the fourth row, and that's 18 wide. We go down to next one 18, and the next one is 32 wide. So there's this nice pattern: 2, 8, 18, 32. Have you possibly seen that little numerical sequence somewhere? And the answer is yes, of course you have. That's the number of electrons that you can get into the first shell, right? 2n squared, 2. The second shell, 2 times 2 squared is 8. The third shell, 2 times 3 squared is 18. And the fourth shell, 2 times 4 squared is 32. So there is a relationship simply on the periodic table between how many elements there are in a particular row and how many electrons you can put in each of those subsequent shells. And so you would expect there to be, because of course what you're doing when you put electrons in shells is you are increasing by 1 each time the number of electrons in the model. And when you look at the periodic table, of course, as you go from one element to the next, those atoms are increasing by 1 proton, which means the atoms are also increasing by 1 electron. So straight there's that nice little relationship associated with the rows versus the shells. Now let's move helium over there. You feel sort of sorry for helium. Hydrogen and helium are both kind of lonely little atoms. They're weird, they're strange, because they are so small. But we can move helium over there. And once we do that, we have a nice little blocky pattern of the periodic table. If you look first of all on the left, there is this block here that is 2 columns wide. Okay? Then the next block we come to here is 6 columns wide. And now the next block that we get to in terms of numbers is this one, which is, count them up, 10 columns wide. And then finally, this block down here that, if you remember, we had to pull out from the middle of the 10 column wide block just to make it easier to put the periodic table on a piece of paper. But anyway, that block there is 14 columns wide. Now, hopefully you see that nice little pattern, 2, 6, 10, 14. We're increasing by 4 columns each time. Okay, and now even more so when you break the periodic table down in terms of those columns and their rows. The first row, 2, is of course just one of these columns here in the so-called labeled S block. The 8 wide, so that was the second and the third rows of the periodic table, where 8 is equal to 2 plus 6. 2 for the S block, 6 for the P block. 18 is 2 plus 6 plus 10. In other words, 2 from that S block, 6 from the P block, and then 10 from that D block. And then when you get down here, 32 wide, well, that breaks down into 2 for the S plus 6 for the P plus 10 for the D plus 14 for the S. Okay, so the rows themselves correspond to the number of electrons that you can put in each successive shell. The columns can be broken down into these 4 nice blocks, and then we can take the rows, which correspond to the shells, and break them down into the block contribution, which is effectively what we'll be doing when we break them down into subshells. Because the subshells that we're going to do are, we're going to break those shells into an S subshell, a P subshell, a D subshell, and an F subshell. First shell, only 2 wide. We only need to make that part of an S. The second shell, on the other hand, we can get 8 electrons in. How do we build up 8? 2 for the S, 6 for the P. The third shell can put 18 in there. How would we break the 18? 2 for the S, 6 for the P, 10 for the D. And so the third shell has 3 subshells for it. And then the fourth shell has 4 subshells for it. S and P and D and F. 2 from S, 6 from P, 10 from D, 18 for F. So that's how we're going to use the periodic table. Break the periodic table down into, first of all, shells, which correspond to rows, and then subshells, which correspond to the particular blocks. Now, you don't have to memorize a huge amount of stuff, but you do have to memorize a few simple things about breaking the periodic table down into these blocks. So here we are, S block, P block, D block, and F block. Okay, well, if you think how we're breaking down the shells into subshells, the first shell broke down into the 1S, and that was it. The second shell broke down into the 2S and the 2P. It had an S and it had a P, so we call it the 2S and the 2P. The third shell would have the 3S, the fourth shell the 4S, and then we go higher, 5S, 6S, and 7S. So these rows of the periodic table in the S block correspond to the first shell, second shell, third shell, fourth shell, fifth shell, sixth shell, and seventh shell. The S block starts at 1S. Every single subshell has an S subshell. Every single shell has an S subshell. Going on to the P, well, the first time we saw P was not in the first shell, it was in the second shell. So this first row of the P block is called the 2P. Okay, it's a P subshell that's in the second shell. And then, of course, once we got that, there will be a P subshell in the third shell, a P subshell in the fourth, a P in the fifth, a P in the sixth, and a P in the seventh. Okay, now something that will confuse people kind of often, okay, is here's the D block here. Now, the first shell doesn't have a D subshell. The second shell doesn't have a D subshell. The third shell does have a D subshell. So the D block starts at 3D, even though you might say, wait a minute, we're into the fourth shell here, the 4S. Yeah, well, don't stress about that, as we see as we'll go through. There is no reason why we can't start the fourth shell with the 4S before we finish the third shell with the 3D. So anyway, this first row corresponds to the 3D. The second row of the D block is the 4D subshell, then the 5D subshell starting here, and the 6D subshell starting there. Finally, the F block. Well, there wasn't an F subshell in the first shell. There wasn't an F subshell in the second shell. There wasn't an F subshell in the third shell. There was, however, an F subshell in the fourth shell. And so the F block starts at 4F. So 4F with cerium here going through lutetium, and then 5F thorium going through lawrencium. So what we can do is we can break the periodic table down between the rows that correspond to shells, the blocks that correspond to subshells, and we can identify different parts of the periodic table using those subshell notations.